Warm welcome to all the speakers and honorable coordinator and the participants. We have a very able speaker today. Already the participants has experienced his vast and profound knowledge. Mr. Pradeep K. Shin Sharma, who had his Bachelor of Chemical Engineering from Jadavpur University, MTech, and he was a silver medalist in Jadavpur University, that is stood second. And MTech Chemical Engineering from IIT Kanpur, and having 38 years experience in oil and gas in India and United Arab Emirates. So you are very much familiar with his style of delivery and the profound knowledge. He was our keynote speaker on the inaugural day. Then you had one lecture that is a few days back, and it was a very, very exhaustive session. And today, again, we have got him, Mr. Pradeep Shin Sharma. I think Mr. Shin Sharma will speak on the safety aspects in oil field, isn't it?
Yes.
Yes.
Safety.
Surely. And we also have our coordinator, Mr. Oshanendu Mondal. Both of them were colleagues at some time. So this is the very basic background, and then we will have one officer, the production manager from Indian Oil. His lecture will start around 7 o'clock. Mr. Mirza Altonia. So over to the mic to Mr. Pradeep Shin Sharma.
Yeah, thank you very much. Good afternoon, Swami Vedgananandaji and Mr. Asananda Mondal, and I think rest all our students, I guess. As I see, there are some 17, 18 participants. Are you expecting some more, or it's all?
I think so. Meanwhile, since I have seen that Kakuli has also joined, so my request is if it is possible to have one recording, because we are having the live streaming, but that includes so many things, so that we can get only your solo lecture, which we can share somewhere. Okay. So if it is possible.
She has joined. I think Pallavi joined in from Kakuli's machine here.
Oh, I see. Okay. So Pallavi can also do that, the same thing, if it is possible. No hardship.
If they're ready or not, I don't know. They may not be ready. I don't know. Oh, they're from the another room. I don't.
Oh, I see. Yes. No problem.
I'll see. Okay, so maybe we will start this one, and I'll see if in between you need some break. Okay, I think it's almost maybe 1 hour, 1.5 hours. Now, the subject today is HSE in oil and gas, safety, health, environment in oil and gas. And my friend Asananda Mondal and me, we worked for many years in oil and gas industry together in ONGC. And I'm sure he'll agree that oil and gas starts with safety and ends with safety.
So, yeah, that's true. Yeah,
it is basically in the DNA of oil and gas people, and safety has to be in the topmost priority, topmost in your head. Whatever you do, whatever steps you take in your workplace, in your home, in roads, in streets, everywhere, safety has to be the topmost priority and topmost on your head. Now, to talk about safety, it is such a vast subject. I cannot do justice. I cannot touch everything about safety in oil and gas in 1 hour or so. But I'll try to just give you some glimpse of what we do when we talk about safety. in oil and gas. And from there, that may be a diving board for you to explore further. So before I start, maybe can I see some cameras on? I mean, I can just see the faces of the participants. That will give me some. Yeah, okay. I can see Arup Kumar, Sayan Mukherjee. Who else?
Good afternoon, sir.
Good afternoon, Sayan. How are you?
Good afternoon, sir. I'm good, sir.
Good afternoon. Good afternoon, Arup. Anyone else having camera or all without camera? Don't worry, I'm not going to catch you in the camera, no problem. You can connect your camera, you can put your audio on if you have a questions anytime. And if you do not have questions, if you don't ask me questions, then I will ask you difficult questions. So it is your choice. Okay. And it is, I think it is an internship, and probably they will be marked. Huh? If the answer good, their marks will be better. Okay. Now let me see my presentation where it is.
I think even if the marks are not better, their future will be definitely better. That I can say. Compared to others.
Okay. How to present? Where is that? Share screen. Okay. Now, just let me know when you see the screen. Okay. You can see it, no?
Yes, sir.
Okay. Okay. Today's subject, as we said, it's HSE in oil and gas. HSE means health, safety, environment in oil and gas. Now, before you jump into this health, safety, environment in oil and gas, let me tell you something. This HSE is not a subject by itself. Huh? HSE, everything in HSE is basically stems out from common sense. Common sense backed by your technical knowledge or any knowledge, common sense by your knowledge, you can be a HSE master. You have to apply your common sense, and it can be backed by your technical knowledge. Knowledge is also very important. So it's nothing but common sense. And before we proceed further, let me just ask you some question. Can you spot some hazards in this picture? This is a kitchen. Probably you have similar kinds of kitchen.
Hand gloves in gas oven, sir.
Very good. Hand gloves, gas oven, yes. Then,
sir, knife above the child's over the knife.
yes, knife is not properly stored in proper place. Very good. Go on.
So water spilled all over the floor.
Very good. Good observation. Then you can speak. Anyone, you can speak even if you do not have the camera on. Come on. Okay, 3 is already.
Sir, microwave door is open, sir.
Yes, oven door is open. And then.
Sir, the lady handling the knife in a wrong way, sir.
Maybe a wrong way, but she is left-hander, I think. So maybe.
No, actually, she's handling the. Picking the knife not in the handle.
Okay.
Sir, the sockets of the apparatuses are inserted, which are not even in use. Which are not in use.
Not in use, maybe, or maybe there is too many sockets in one plug, huh?
Yes, sir.
Okay, very good. You have got most of the things. Maybe 1 or 2 are left. Okay.
So toys spilled over the floor of kitchen.
Yeah. That is liquid spilled. That was spoken, I think. What else? I have some more. This guy is doing something here. Is it okay here? This is a place to do this cluttering of these things? No?
No, sir.
Okay. What else? What about these things?
Yes, sir. Toys are spreading over.
It's
In the
spreading
kitchen.
over. So if there is something this lady wants to come out of it, she might trip over it.
Yes, sir.
Is there anything wrong here?
Sir, knife stand.
No, you can see my cursor.
Yes, sir. Water is flowing, sir.
Yes, so wastage of water.
Right, sir.
We don't notice because some of us are guilty of just keeping these taps on and don't understand that we are wasting our valuable resources. I think you caught most of the things. Maybe one or two more are there, which is here. Okay. I think you got most of the things in this on this. This is the thing which we didn't speak about. This mutton is on this. It should not be on this table. Okay, food should be on this board. Okay, and I think all others you have spoken of. Maybe another small exercise. Are there any hazards here? This is your office.
Sir, the blizzard is hanging in a wrong way, sir.
Blazer hanging wrong way. Yes. Okay. Good point. Then.
So, the drawer is open, sir.
Yeah, drawer is open. Very good point.
Sir, the wires are all over the floor.
Yes, wires are all over the floor. It can get caught, and this is not the way. Wires should not flow, pass over the floor. Yes.
What is that, sir, near the cup?
Sir, the coffee mug should.
Coffee mug should. Near the coffee mug. What is this? This one you are talking about?
Yes, sir. Yes, sir.
This is a paper cutter. Is anything wrong with this?
Paper cutter.
Yeah, okay. Let us see then. I think you caught many of those. Now see which one you didn't catch. Paper cutter, that blade is up, and that is a very dangerous position. Huh? Blade should be always down and locked if it is not in use. You got this drawer right. You got cables right. Yes. The coffee without lid. Okay, this is he's working here. Okay, this I don't think we pay a lot of attention here. This coffee near these electronic machines and all, this can spill over and it can cause problem. Normally they suggest you should have a lid over this. File drawer left open, you already told. Computer monitor is very high. What should be the normal position of the computer monitor?
Level of your eyesight, sir.
Level of your eyesight. Then space heater near flammable material.
Yes, sir.
This paper, okay, can catch fire. Improper chair. What is improper chair? Too low backrest, too low. Okay, it's not getting properly rested. Cords running on the floor, already told. Now I have shown you something on the household things. Okay, what is the relationship with oil and gas? There is a very big relationship here. Whatever you notice here, if it just tells about your safety consciousness. I told safety is general knowledge, just common sense. And you apply these common senses in oil and gas. In fact, in the end of the design, any oil and gas facilities also will have all these things. There will be kitchen for people, there will be offices there. And in the design of the facilities, all these things are also taken care of. So oil and gas design is not related to oil and gas only. It is related to people also. Okay. So all these things, you have to sharpen your HSC common sense, and then you can apply your brain very well in the oil and gas situations.
That is basically related to the ergonomics.
Yes, this is ergonomics. This one, yes, something is related to ergonomics and something is related to substandard practices. Something is related to maybe design. You should not place this here. Okay, these are ergonomics. This chair low, this one is there. Okay, the ergonomics itself is a deliverable in oil and gas projects. Okay. Now I saw Arup,
Yes, sir.
yeah. You have a fan there. Is it too hot now?
What, sir?
You have a fan in your room, no?
Yes, sir.
So is it warm, hot now? It's raining, no?
No, sir, it is not raining.
Okay, so it
Little
is
bit
still
hot,
hot. So you need fan there. Okay. You have any problems with the fans? Or do you think that these fans can give problems?
No, sir.
Any risk on these fans, ceiling fans, coming from ceiling fans?
Yes, sir. If it hand in properly, then it will be risky.
Yeah, if you put your hands. So that's why they are put outside your reach. But even if you do not put your hand, there may be some problems coming out of the fans. Just a short video I can show you. Can you see?
Yes, sir.
Providential escape. Providential escape, isn't it?
Yes, sir.
So these fans can come out of it, okay? And if you, by the way, whatever I'm showing you, it's all available in the open, YouTube or anywhere. You can go, you'll find all these things. And if you look for these fan accidents, there is not one, there are many. And these kind of things can happen, this ceiling fan, okay? So there are so many things that goes into the design and the installation of the fan also. So design of the fan should be such that it can take its load on load. And during installation also, you have to take care of so many things. A very simple miss, maybe that lock nut, there is a pin there. And that is a very common miss sometimes. They don't put the pin correctly, but just put it and don't bend it. So this can create this kind of incidents and accidents. So even if you're home, you should take care of these things. That whenever you are installing the fans or somebody else is installing the fan, you must take care that they're installing it properly so that this kind of accidents cannot happen. So you, first is by design, then by workmanship, by training. Man who is installing that fan, he should be trained. He should know how to install it. And then periodically we should check, because there can be material failure over a period of time and all. This is a home example. And these are same things we do in oil and gas. We take care of the safety during starting from the design all the way up to operations and up to the end of life of this plant. We do these things. So safety starts from home. Now coming back to safety in project. Now when you talk about that safety in oil and gas, now when you talk about oil and gas facilities, it has a big life cycle. Big life cycle means first it will go through a project to bring the facilities up. In the project also, we have got many different stages. And the safety starts right from the day one when someone even thinks about starting an oil and gas project. So it starts with project stage. We normally define these project stages or segregate these projects in 5 different stages. We call it in our place here, we call it as assess, select, define, execute, and operate. These 5 stages. Different companies might give different names, but basically these are the stages everywhere. Assess means you just assess if you need to do a project. That project should give you some tangible benefit It should give you some value addition. Okay, that is the assess stage. Then comes the select stage. Select stage is once you think that project will, that there is a need of going for a project which will add value to you, then you go for select stages. There may be different options, so many different options which you can adopt to go for that value addition to your life or to your company or to your country. So there could be so many different options, and all those different options are analyzed in the select stage. At the end of the select stage, you select a particular option that yes, you are going to go for this project. Then comes the define stage. Define stage is once you selected the option of the particular project, how do you go about the project, where it is, how much you are going to produce, or from which fields you are going to take oil, where it will go, what is its destination, how you will sail and all. So these options, once you select this option, then you go to define stage. Define stage is you do further engineering to define the project fully, exactly what are the facilities you will have and how you are going to operate the field, from where you are going to get your input, where you are going to sell your output from this, and how you are going to manage the wastes, how you are going to get your energy, from where you are going to get your energy. All these things are defined to the extent that after this defined stage, you know the project fully, that you are going to have these facilities. Everything is defined, including every vessel, every pipeline, every piping, every pump, everything is defined and specified. After that, you go for execute stage. Execute stage, basically you call a contractor. Basically, you call a contractor who will come and do the execute stage. In the execute stage, there are 3 sub-stages. One is the detailed engineering. Each and every equipment is engineered to full detail. Then you procure the equipment, plants and equipment. And then you construct the plant. After you do this execute stage, then the operators come, they do the operation. This is the operation stage. This is the whole life cycle of the project stages. And the end of the operation is, the operation stage goes up to the end, which is the maybe demolition and all, after this life of the plant is over. So these are the basic stages of project. Now, when you approach HSE, HSE is there in every stage of the project. When you approach HSE, the fundamental principle of approaching HSE is, if you have a hazard, then the first thing you think of is to eliminate the hazard. If you have some hazards, maybe your input is something hazardous, or you are using some hazardous, you are required to use some hazardous material, hazardous processes and all. First of all, you try to eliminate that and try to adopt some other things which is less hazardous or non-hazardous. The next one is you replace that hazard, substitution. That hazard you replace with some other things which may be less hazardous. If you cannot do these sufficiently, then the third stage is engineering controls. You put all engineering controls to isolate people from the hazard so that it does not harm people. Then engineering controls also will leave some holes in it. So that you plug with administrative controls. Change the way people work. So you train the people, you make them understand the hazards and all, and you change their way of work so that they can take care of the hazards which are there. And finally, after all these controls, if there is a hazard, if there is an escape of these hazards, then you use personal protective equipments to protect people from the hazards which is already exposed. So these are the hierarchy of controls we use in HSE. Now, what I'll do is I'll just go through a very small part of your oil and gas plant and how we go about it, how we design and how we put safety in it. Now, when you talk about the safety, there are basically two categories, two major categories of safety we talk about. One is process safety. Process safety is within the process plants. Within the process plants, you take care of these process elements in a safe way. And another is personal safety or occupational hazards, safety from that. So when you talk about the process safety, first this during the design stage, okay? This is a small plant. I will just explain how we take care about the process safety, which most of the process engineers will have to take care. When we talk about safety, sometimes we tend to think that, okay, safety, maybe some safety engineer will come and take care of this. I'm telling you, they will not do anything. It is you, as if you are I think most of you are chemical engineer by profession, so you'll be probably, some of you will be coming to the process engineering, and safety is your cup of tea, not safety engineers. Safety engineers will be always in advisory roles. They have a very important role, and mostly chemical engineers go for safety engineers, or even all other discipline engineers also go. They will think about safety, they will give you advice. Their advisory roles, they will give you all the codes and standards, recent development, the codes and standards, and guide you how to deal about things or how to enhance safety. But finally, the elements which you put for process safety is your responsibility as a process engineer, not safety engineers. So what I'm explaining is all process engineers' job. Now this is a separator, three-phase separator, which is a very simplest and most basic equipment in oil and gas. I don't know, you have read in any of your courses, oil and gas separation particular?
No, sir.
You have not read. Okay, so just simply let me explain what happens. Three-phase separator, when you talk about oil and gas, whatever coming from the reservoir, from the wells, is having oil, gas, and water. So oil, gas, and water. Gas is lightest. Oil is in between 0.8 to 0.85, 0.86 density. And water is heaviest, 1.03 to 1.1 sometimes, okay? So how they can be separated? Simple gravity separation. Everywhere it is done gravity separation, but sometimes that gravity separation is aided by other means like heating. Heating reduces the viscosity and all, it aids in separation. Putting electrostatic field, that also aids the separation, but finally it has to be a gravity separation. So this is a very basic thing. First thing which we have in the oil and gas field is a three-phase separator. So in the inlet, well fluid means the fluid which is coming from the wells, from the reservoir is coming. This is basically having oil, water, and gas. So what happens? The water will be settling at the bottom, oil in the middle, and gas at the top. And there are some internals inside to aid in this separation. And finally, what will be there? Water will be taken out from a separate nozzle. Oil will be through another nozzle. Oil will overflow to where and go to another side, other side, to the oil side. And then gas will go through a gas outlet device into there. So this is a very simple process in a separator. Now, inlet is coming one and outlets, there are three. So you have to have a lot of controls in this. Controls in this, finally what you will have to do, whatever comes to the inlet has to go out. You cannot accumulate inside this indefinitely, okay? In a steady state operation, whatever oil, gas, water comes in has to go out through these three outlets. So how do you ensure that? You put, the basic design is you put control valves in all these 3 lines. What it will control? The gas. Gas is at the top. Now, if you let lot of gas go out of the separator, what will happen inside? Inside pressure will decrease. And if you close that gas outlet, what will happen? Pressure will increase. So this gas control valve has to be operated by a pressure controller, pressure transmitter and pressure controller that will operate this gas control valve. If pressure increases inside the separator, the control valve opens. If pressure decreases, control valve closes. So it maintains the pressure by the PCV in the gas line. Oil outlet, oil, it tries to maintain a level inside the separator so that whatever comes in goes out. So if level increases, this level control valve opens, level decreases, level control valve closes. Similarly, water also, by level, water level. And they are on 2 sides of wear plates. So this side water level is maintained by this. This is not PCV, this is LCV, okay? We call it interface level control valve. So this is a very basic control of the separator. And if everything goes okay, steady state, no problem, okay? Now, there is no safety here as such. Till now, we have not talked about safety. We have talked about the process control and everything is flowing. But in actual practice, this will not be like that. There will be so many disturbances. Maybe this fluid which is coming from the well, there is a lot of changes in this fluid. That flow can increase suddenly or it can decrease suddenly because you do not have much control over what is coming from the well. And that too after the end of a big pipeline. So there is always fluctuation of flow rates in here. So these fluctuations can cause all these things to go high and low. Pressure and levels can go high and low. And it can so happen that these control valves are not sufficient during that time. Maybe this one. Say too much of input is coming, gas, too much of gas is coming. And this pressure control valve goes fully open, still a lot of gas coming. It is beyond the capacity of this pressure control valve. What will happen? Pressure will go on increasing. Now this separator has got a design, somewhat some design pressure, and we normally operate close to the design pressure, maybe 10%, 20% lower than the design pressure. We have some margin, but we don't have indefinite margin. So what will happen if pressure goes, increases, then it can fail the vessel. We cannot let that happen. So we have to put some system which will avoid this pressure to go beyond its design pressure, beyond its maximum working pressure. What we do? Okay, first of all, here I have shown a gas going out to a compressor. One of the reasons by which this pressure can go up is maybe this compressor stopped. So what I'll do, I'll put another control valve which will send the gas to flare. There is always a flare in oil and gas field, which is normally is pilot is kept on, and gas will go to the flare and will flare temporarily till the compressor comes back. But this control system can fail, or there may be too much to the inlet by which this pressure is increasing. Then I have to put a safety. What is that safety? Based on this pressure, what I have to do? I have to choke the inlet. I have to cut down the inlet if pressure keeps on increasing. So what I will do? I will put a shutdown valve at the inlet, which will operate on this pressure. Well, beyond certain pressure, it will close this valve. So now my separator is safe. It will not increase further in the pressure. Okay. So this comes as a process safety. Okay. Similarly, if the oil level keeps on increasing. Before increasing, let me check. Say oil level, LCV goes fully open and it is not getting closed for some reason, or there is a passing leaking through this and there is not much input. So this oil will go, level will go low. What will happen? Gas will go into the oil. which can be dangerous depending upon what we have in the downstream. This situation we call gas blow-by. So what will you do? You will put a shutdown valve in the oil line, which will operate based on the some low level of oil. It will close this shutdown valve. So it will save this from this side. Now I have clicked again and another shutdown valve came here. What that is doing? That is doing other side. If the liquid level say keeps on increasing, and maybe this LCV is malfunctioning, or downstream there may be pump which has stopped, level is increasing. You cannot let it go. So what will happen? Oil will go to the gas line and it can create big problem in the downstream equipment. So what you do, you close this shutdown valve, first shutdown valve with oil level also. But sometimes what happens is this can be so dangerous, that oil going to the gas can be so dangerous that you need a second shutdown valve also to close. Why? This oil level keeps on increasing, it goes to the gas line. Now you have say you have only one shutdown valve, it tries to close this shutdown valve. There can be always a failure of a single element. There is a basic in the process safety design. A single element can fail. So that failure will lead to this oil going through this gas and it can overpressure also in that case. So you might need to put another shutdown valve here. Similarly, in the water line also, you will put a shutdown valve to take care of the low level in the water. So these one by one, you are going to add this process safety requirement in the separators. And finally, you come out with this. Now, what is there in the pressure design? Pressure design, you have this gas line, gas control valve is trying to control. If it goes beyond certain pressure, it will close the inlet shutdown valves. If this one failure is there, shutdown valve, then what happens? By law or by this regulation, you have to provide a pressure safety valve. So if this shutdown valve does not close for any reason, this pressure safety valve should be able to evacuate this and save our separator. This pressure safety valve operates at certain pressure, close to design pressure, and it will let go all the gas into the flare. Okay, so these are these safety systems inside the separator you put. Now, once you design this, I have just explained a very small part of a plant. Now, this plant is having many pipes, many such vessels, sub-separators, scrubbers, knockout drums, compressors, pumps, flow meters, so many piping, so much of valves and all you have. So you design everything. So there will be a big design and there will be so many drawings generated, which you call P&ID, for piping and instrumentation diagram. So at the end of the design, you do generate a piping and instrumentation diagram, which gives all the details, whatever is there in the plant. In the separator design, there is one more thing. You have to take care of any fire situation in there. Okay. If there is a fire, say at the bottom, what will happen in any vessel? Okay, this is the API requirement. Any vessel you have liquid inside and fire is there, what happens? This liquid will vaporize and it will increase the pressure and it can fail the separator. So in that case, what will do on a detection of any fire, you isolate this separator and you depressurize this separator so that this fire cannot escalate too much. And how do you depressurize? You put a valve called blow down valve. On detection of fire and gas, it will close all the inlets and outlets and it will open this blow down valve to let the pressure go into the flare. So this way it will save your plant from escalating the fire scenario. So these also are to be done by a process engineer. Now process engineer will do all these things. What is his starting point? Okay. The very basic starting point is API, some API recommended practice. Okay, these are very old practices. API RP 14C, recommended practice 14C, is one of the things with which you can start designing this plant. It will guide you what are the process safety systems you should put into different kind of equipment. I have shown here a pressure vessel like a separator. It says that it has to have a high level safety, it has to have a low level safety, it has to have some flow safety. By the flow safety is check valves. It prevents flow in the opposite direction. It can have a temperature safety if there is a heating element, beyond that. Every vessel, it has to have a pressure safety valve. It has to have a high or low pressure sensing. So these are general guidelines given in the recommended practice, API 14C, that should be your springboard to start designing process plant. That same API 14C will give you a safety analysis table, which lists the undesirable event and what could be the possible causes, which you have to look after into the design. And then how you detect those situations on the right side. What are the detectable abnormal conditions? How you detect those situations so that you can take appropriate action. You can install appropriate sensors and you can take appropriate actions depending upon the sensors reading. It will give you finally a checklist, safety analysis checklist. In a pressure, this is for a pressure vessel. It has got for all different kinds of equipment. I'll just put a pressure vessel safety analysis checklist here for an example. That the high pressure sensor, how do you take care of a high pressure situation? What are the different things that will be preliminary acceptable, either a PSH or there are other things that the protection is there somewhere else, so you don't need a PSH here. So it will give you what sort of things you can put here and whether you have put it here. Okay, so this safety analysis checklist will allow you to confirm that your design has taken care of this high pressure situation, low pressure situations, then pressure safety valves also, whether it is required or not, high level sensors, low level sensors, check valves, high temperature sensors. So these things you can get from the safety analysis checklist to check if your design is okay or not. Now you have designed the plant with API 14C as your weapon. You have designed the plant, but this is the very first preliminary design. Now it has to go through a detailed analysis, and the most detailed analysis in a process plant is done through a HAZOP study. It's called hazards and operability study. The full phases, you develop the full P&ID, piping and instrumentation diagram, which defines every vessel, every equipment, every compressor, pumps, valves, and all sizes are given, all material is given. Okay, and then taking this whole sets of P&IDs, a study is done which is called hazards and operability study. The study simply asks the questions. If there is a high pressure in a particular section of the plant, what are the causes of the high pressures? What are the consequences of the high pressure? What are the risks from this? And then what are the protections which you have already put in the design, whether they are sufficient or you think that there are some more protections which need to be done. So this is done on these guide words: pressure high, pressure low, flow high, flow low or no flow, temperature high, temperature low, level high, level low, all these things individual. These are called guide words. Through these guide words, we ask the question to each section of the plant. First of all, the full plant is divided into different sections, logical sections, and each section is studied with all these questions in mind. So say this is a P&ID you develop, okay? Short of P&ID, it tells what is the vessel, what are the vessel inside, where are the pressure transmitters, all these things, level control valves, all these things. This is just a part of the P&ID. And that whole sets of P&IDs, sometimes in a process plant, you can have probably 150, 200 P&IDs to define a section of the process plant. And you divide those whole section into different logical sections. I'll not detail into what is this logic, how these logical sections are defined. It will be too detailed. And then you apply certain guide words as HAZOP. The guide words could be high level, low level. For a separator, say example, for a separator, high level, deviation is high level, means separator, there is the intended level at which you will be operating, but now high level has occurred. So high level, what could be the causes on the high level? What are the consequences on the high level? What are the safeguards you have already put? And then it will do a risk ranking also in the HAZOP. The risk ranking, it is called a risk analysis, risk assessment. It will do a probability of this high level happening and the consequences, what can happen due to this high level. That also, it will do the severity of those consequences. Now this, I don't know if you are anyway accustomed to this risk assessment. Let me just open a risk assessment matrix here. So what happens if there is a high level? What is the probability? These are the qualitative analysis you do. These are the probability matrix. Increasing probability has occurred in industry, has occurred in operating company, occurred several times, or occurred several times in the same company. These are the qualitative probabilities. And then these are the consequences. Now, in the consequences, normally we take care of 4 different types of consequences. Consequences on people, means it can cause harm to the people. Consequences on asset, it can cause the asset damage, means separated damage or downstream or upstream damage. Consequence on environment, that means oil and gas can go to the environment, there could be fire and explosion. And consequence on the reputation of the company. Okay, sometimes reputation is very expensive for companies. Okay, so these consequences also have got different levels of consequences. And depending upon, in the HAZOP is done through a multidisciplinary team, and they discuss what can happen if this level goes high. It can come up to the flare, it can go out and all, and what should be the final consequences? What can be the final consequences? With this, they will decide for each of these 4 types of consequences where they can place this particular incident, and then this multiplied by this, it will give you where you are in the risk matrix. In the risk matrix, there are 3 different regions. One is high, red. If it gives you in the red region, then you have to change the design. You have to do something to come to the yellow region. Yellow region is, it is acceptable, but you should go down to whatever extent possible. And green region is, you don't need to take much any further action. So this way, in the HAZOP, you analyze each and every situation and do the risk ranking here. And then check what are the safeguards, and qualitatively you analyze whether these safeguards are okay or you need other safeguards. So this is the way you do HAZOP. This is also a safety study. HAZOP is a safety study. We call it process hazards analysis. Okay. So you do HAZOP, you apply these guide words, and you do this high level, low level, high pressure, low pressure. For every possible parameters, you put the deviations and you do this kind of analysis. It will tell you whether you have taken care of this hazard sufficiently or you need further actions to be taken, which will be stated in the recommendations column. Now, once you go out of this HAZOP, these recommendations, whatever comes out of the recommendations, you put in the design. There may be some changes required in the design. So you do that design, and finally you update your P&ID. Now this is HAZOP and it is supposed to be safe. Now next is, you have put so many control things, so many controls like this. This one, shutdown valves getting closed on a pressure transmitter. This shutdown valve is getting closed on a level transmitters. These are all done by instruments. So they're called instrumented protection system. And these instruments of protections, they have so many elements in this, the transmitters, the controllers, and there are transducers, and then the final element, which is the valve that will close or open. So these instrumented protection system analysis is done through analysis which is called SIL, safety integrity level of these instruments. So this HAZOP is always followed by a safety integrity level assessment. Now this is too detailed. Too detailed means what happens is the each and every safety instrumented function, like a level high switch is closing a level shutdown valve, level oil line shutdown valve. This is a safety instrumented function. Each and every of the safety instrumented function is analyzed to check what is the requirement of integrity level of that particular function and what you have already. And this instrumented function, a particular factor is defined, which is called a probability of failure on demand, is defined by the safety integrity level analysis. So this will tell you how robust you should design that instrumented function. So the robustness of that is decided by this SIL level, that you need this much integrity level of that safety integrated function. I'll not discuss in very detail because this will be too detailed analysis. Ultimately, you arrive at a level of this safety integrity of that particular function which is required. And there are generally 4 levels of SIL which is assigned to this instrumented function: SIL 1, 2, 3, and 4. And normally in oil and gas industry, you don't go beyond SIL 3. Even SIL 3 is complicated. Beyond SIL 3 is much more complicated. Probably only in nuclear industry you have SIL 4. Oil and gas industry, you will not have SIL 4. If you come out with a requirement of a SIL 4 of a control system, then you have to mandatorily change the design. You cannot go to SIL 4. There will be too detailed requirement and that is too dangerous. So once you decide this, then you decide detail of these instrumented functions, how to go about it. Okay, and then this process design part is more or less complete. You have designed everything what is required there and what sort of instrumentation is required to control your process safely. Now, this is only process safety, okay, as a process engineer you'll do. But there are many other process HSE works, project HSE works done, many other. I'll tell you what are the kind of project HSE deliverables, means what sort of documents and what sort of studies are required in project HSE. Now, what is the principle? Principle of designing a safe system. Your basic idea is to prevent any accidents. Prevent any accidents means prevent any oil and gas escape to the environment, prevent any fire, prevent any blast, blowout, or whatever. Your basic idea is to prevent accidents. Now, this is a bow tie. You know bow tie, some of you must be wearing. Now, accident is the middle. So accident can happen due to some causes. The causes are on the left, okay? So there could be many different causes for the accidents. So we pick up a top event, any event like gas leakage, explosion, okay? Some vessel damage, something. And we analyze what could be the causes. What could be the causes which will lead to these accidents? And then, if that accident happens, what are the consequences? Consequences are on the right side. It can harm people, it can harm asset, it can harm environment, or it can harm reputation. So that there will be many causes causing an accident, and due to this accident, so many different consequences can happen. This looks like a bow tie. Now, the principle of safety is first, all your efforts should be on the left side first. You should try all out to prevent this accident happening. Or am I correct? Or you think on the other side you should focus more first? That let the accident happen and we will take care by putting something here so that it doesn't harm people, environment, and plants. Anyone can come back. Which side we should focus first, left or right?
So left one, sir. We have to prevent the causes first.
Okay, so you agree that we should focus on the left side. Okay. So first, all our efforts should be on the left side. There will be so many different causes. And how do we prevent those causes reaching the accident is putting barriers, one after the other barriers in those. In the next slide, I'll just explain some of the barriers, how it is done. So like we analyze different causes and we put barriers one after the other to make it difficult to reach this spot. But even after putting all those barriers, these energy sources can find some ways to cause these accidents. Then also, even if we put all those barriers, nothing is 100% guaranteed in the design and operation anywhere. So you can still have accidents. Then you should put the right side barriers between the accident and these consequences so that it doesn't harm the people, it doesn't harm the assets, it doesn't harm the environment, or it minimizes those. So full focus on the left side, and then to prevent the accident event, and then you shift your full focus on the right side also. Right side also, you have to put full focus after you take care of everything on the left side. So this is the way this HSC design goes in each and everything. We call it a bow tie diagram. Let me see. This is an example. Okay. This is loss of containment. Okay. Of a oil in a turret. Okay. It says different kinds of failure which can happen. Mechanical failure can happen. Corrosion can happen. Erosion, process conditions exceeding design limits, inadequate overrides or exhibits, vibration, mechanical impact, human error, severe weather. These are all different causes which can lead to these accidents. But now we can think of different barriers between these causes and this accident. Example, mechanical failure, we can select equipment selection per standard. We should be following standards properly to have proper equipment selection. This is a barrier in between mechanical failure and this accident. Then we'll do a flange management procedure. Normally in mechanical failure, the most common location of a failure in a plant is flange. We'll put flange management procedure, properly manage this flange tightening and all, so that we prevent any leakage and loss of containment. And we'll put people for site monitoring also. Site monitoring means when you have a loss of containment, in most of the instances, that loss first starts with a very minor leakage. And if you have a proper site monitoring, you'll catch it then and there itself before it escalates into this top event. You can take care. You can take that unit out and then do this repair and all, whatever. If there is a gasket leakage and all, you do that repair. So you put all these barriers to prevent this accident from happening. For corrosion, you do a proper material selection. Then you do a corrosion management study. Maybe you have to measure the thickness very regularly. So you have to put up a plan for thickness measurement. Then probably you have to use corrosion inhibitor chemicals. Then you have to do site monitoring and then whole asset integrity monitoring. So this way you can prevent a piping or vessel failing due to corrosion, causing this loss of containment. So this is an example how we can put one after the other barriers. And in the boat end, every barrier we put, these barriers can also fail. And there could be different reasons for which these barriers can fail. Okay. So we put a barrier in those reasons also to make this primary barrier work. I'll give an example here. What is the process shutdown system? We have put process shutdown system like say pressure increase, closing the inlet valve. But it may so happen that that pressure transmitter may be under maintenance during that time. So you have bypassed that pressure transmitter. So that inadequate override, bypass means override. If that is overridden, then this barrier can fail. So we have to put a proper override control procedure, and we have put competent operators so that this failure cannot affect this barrier. So these barriers, we have put sub barriers so that this main barrier can work. Similarly, on the right side also, once this loss of containment happens, it can have fire explosion resulting in fatalities, personal equipment and all. So we can put barriers. What are the barriers we can put? Equipment selection and installation for hazardous areas. Now, loss of containment has happened, means gas has leaked out. How it can catch fire? Between containment loss and catching fire, there is another thing in a fire triangle, which is a ignition source. So prevent ignition sources happening there. In a plant, there are so many ignition sources can happen. There are electrical equipment which could be the ignition sources. So this barrier is select those electrical equipment based on the area classification so that you eliminate that ignition source. Then, okay, if there is ignition, fire and gas detection facilities, immediate it will detect, it will do general alarm, and it will ask people to escape to a temporary refuge so that you are saving people here. So you are saving personnel by these barriers. Now, temporary refuge, it can fail. Maybe in the escape route, there are so many things put, like we saw in that kitchen. In the escape route, so many things are put. You may not be able to escape. So alternative escape route should be there. Okay, so this barrier can be put between escape route impaired and this so that this main barrier can work. So this is the way bow tie analysis is done for the whole platform. And in a process plant, if you see this bow tie analysis, it will be a very big and very, very complicated because each and every element is analyzed, each and every sub-element is analyzed, and finally it becomes a very big file. I've just put a one part of it, which is easily available in the open internet. And in actual plant, this bow tie diagram will be very, very complicated and very big, where you will have so many different barriers which are put. Some of them are procedures, some of them are designed, okay, and some of them are this monitoring. So all these things are put. Some of them are maintenance. So all these barriers are put on the left side as well as right side. So this is the principle on which this HSE works there. Now, as we said in the beginning, I said there are 5 stages in the process: assess, select, define, execute, and operate. Okay. Up to execute, it is the project design. And there are different kind of HSE deliverables, means HSE studies, reports are done during different stages of the project. Assess stage, HSE plan, environmental baseline study is done. Then health safety impact, environment impact assessment is done. This is a very important document to get government approval. You must have read many projects are shelved because of problem on environmental impact. This impact assessment will give that what sort of impact, whether government will accept it or not. And this is also a very important document here. In every country, this is an important document for going ahead of any project, government approval. Then PHASA report is basically this project health, safety, environment review, whether we are doing all the required safety studies or not. This is also a mandatory requirement in a project. In the select stage, we do much more than asset. HSE philosophies, HSE IA, all those things are revisited. Then risk management documents are done, HSE plan done, risk register. There is a hazards identification study. This is also a big study in the beginning of the project, where we normally identify all major hazards and how we mitigate those hazards. Then PHASA report, and there is a quantitative risk assessment also done in those. Quantitative risk assessment, basically, it is a study which will give some figures of the risks on individual people who are involved in the project and operations, and also on the risk on the, it is called societal risk, group of people within the plant and outside the plant also. And that is also an important document, and every company has got some acceptability criteria of those risks, and check this project, particular project, what sort of risks it is creating for the individuals and society. Okay, so this QRA gives that. And then define stage, you have very many different kind of documents and studies done in HSE. Too detailed study. Someone was talking about this ergonomic study, that chair was not good. This ergonomic study is done here also. You would think of any HSE studies, anything, it is done in this environmental baseline study. It develops HSECES. Remember this word. If you go to plant in any process industry, you will hear about this: health, safety, environment, critical equipment systems. So it develops a list of those HSECES. HSECES is basically the equipment and system which either prevents accidents, incidents, or mitigates. So those are the barriers we are talking about on the left side and the right side of the bow ties. So a list of those are developed in the define stage, and their how to maintain their performance standards are defined. And there is a document called written schemes of examinations, how they will be examined. And they're all basically all their maintenance standards are also developed, which we have to take to the operate stage to follow. Okay, I have just put in red because these things are required at the operate stage also. CMMS data of HSECES, this computerized maintenance management system data of HSECES. Maintenance, we have to maintain all the equipments which are critical for maintaining the HSE. That is the barriers which I talked about. So they are maintained through a computerized management system. Okay, I put in red because all these things we have to use during the operate stage. Then this is the define stage, and then execute stage, a detailed engineering is done. All that what we have done in the define stage are again revisited in the execute stage. So you can see all these documents in the define stage, plus there are many more. And the red marks things I have marked things, something is red, because those things are used in the operate stage, like a risk register. Risk register, it registers all the different kind of risks and a plan how to mitigate, when to mitigate, how long it will take, and all. This is a dynamic document. In any operating plant also, the risks comes, we take care of those risks, they go out, maybe a new risk comes. So we have to be continuously updating this risk register and maintain the plan. There is a waste management plan which you have to follow during the operate stage. There are cause and effect charts. Cause and effect charts means any particular instruments detected some abnormality. what will be the effect? Okay, what are the causes? Any cause, what is the effect? Like a pump trips. Okay, pump trips, what it will do, it will probably close the outlet, close the inlet, and segregate that pump, close the even the upstream of the separators. So those are the effects. Any cause happening in the plant, what should be the effect? This is a basic document which operators refer day in and day out. Then escape route, master station, and safety signs layout. Inert gas for fire extinguishers, firefighting system layout, we need to know during operate stage. There is a very important document which is called Register of Safety Related Devices. The whole platform, it is a register which has a list of the safety related devices, everything related to safety. Again, those barriers, related to those barriers, whatever, like a pressure safety valve, like a pressure switch, a flow safety valve, shutdown valves. Okay, everything related to the safety is included in this register, which we have to maintain, and we have to check that all these safety related equipments are maintained properly. Then there is the environment management program which you have to follow. There is HSE training, HSE philosophy which you have to follow during the operate stage. So there are, you see, there are so many different kinds of HSE studies and are done, and documents are developed during this project stage. Now come to safety during operation. Am I running out of time? I don't know. What is the time now? Okay.
6:40. 6:40.
Okay. Now during operation, one of the most important thing is permit to work. Now a plant is operating steady state, oil and gas coming, going out, compressor running, pumps running, going out, everything, no problem of safety. The major problem happens when you try to intervene a process. Maybe you have to take out a pump, it is creating noise, you have to take out a pump to do some maintenance. So you have to open some flanges, open some glands and all. Maybe some pump gland started leaking, so you have to isolate that pump. You have to do maintenance, open and fit a new gland, a new seal. So these are kind of interventions. When you do an intervention in a plant, there this permit to work is a must in every oil and gas plant. When you do intervention, then mechanical, the maintenance team comes. Maintenance team comes, they do the intervention, and that has to be controlled very properly, because those are the sources which can lead to incidents and accidents. Those are the activities which can lead to incidents and accidents if not properly managed. So this permit to work, PTW, keep it in your mind, PTW, permit to work, is a very basic process and procedure followed during the operation of the plant. It is basically done in 6, 7 or 8 stages. First, a work request and planning is done. Work request planning means if there is a problem in the plant, or maybe the plant needs some preventive maintenance. There is a list of preventive maintenance actions, means a pump cannot run indefinitely. You have to do maybe an oil change, you have to do some sort of seal is getting worn out, seal life is there, so you have to change it before it leaks. There are so many things you do to prevent any incident happening. So these are called preventive maintenance. And second thing is some equipment has broken down, and then you have to do the maintenance. So those are called breakdown maintenance or corrective maintenance. So any of these things, you have to first do a work planning. So work request planning is done. Then depending upon the nature of the work, we identify and approve the controls required to do that job. The different kind of controls required to do that job. Okay. Then once we identify those controls are put in place. Controls, what kind of controls? Just an example, a pump maintenance you'll do. You have to isolate that pump. You have to isolate the inlet. You have to isolate the outlet. So there is a process isolation. Sometimes you have to do a blinding, SPED, mechanical isolation. Then you have to switch off the power and you have to lock that power also. This is electrical isolation. So there are different kinds of controls are done in there. And then you have to check there is no gas detection and all you have to check, area is clear, and also all these controls are done. And the controls for the people who will be doing the job, they have to use particular tools, they have to use particular PPEs, all these are put in the controls. And once those controls are implemented in the work site, then the work permit is authorized. Then that authorization is communicated and work is commenced. Once work is done, work is ongoing, then continuously people will do dynamic risk assessment. If the situation changes from the original things, then it has to be stopped. So there is a dynamic risk assessment done depending upon any change in the plant. Then after completion of the work can be handed over, or maybe in between it can be suspended, or maybe they have taken a permit for a day, but it could not be completed, so it needs to be extended. So these extensions are done. And at the end of this whole work, the permit closed and the things are handed back to the operation. This is the way it is done. So these are the stages. And permit to work, in a permit to work, in general, there are two parties. One party is the performing party. Another party is the people who are allowing this job to perform, which is the operating party. So performing authority and operating authority. So they sign these permits at different stages. I'm not going to the detail, and they issue these permits. So this permit to work is one of the basic requirement in any process plants during the operating stage. Toolbox talk, okay, it is a detailed thing into the permit to work. Okay, now just show, I think I have some 10 minutes more.
Yes, Pradeep.
Okay.
Actually, Mirza has joined already.
Okay.
So naturally, when you will feel comfortable and I mean, you will almost on the verge of completion, then
yeah, maybe another 10 minutes, because I just wanted to show what is the importance of permit to work. Due to a failure of permit to work, one of the major accidents in the world happened. It was quite some years back, which is Piper Alpha accident. I think you must have heard of many. If you not, it is a 3-minute video.
July
you can
6,
just see.
1988, 120 miles northeast of Scotland, the Piper Alpha oil rig. At 14,000 tons and 2.5 times the height of the Statue of Liberty, it is one of the largest rigs in the world.
Piper Alpha was the world's most successful oil rig. What that means was that in a single day, Piper Alpha produced more barrels of oil than any other oil rig or oil platform in the world.
A crew of 226 rotate shifts to keep the oil and gas flowing. Jeff Bollins is the chief control room operator that evening. At 9:45 p.m., Jeff suddenly hears an alarm, indicating a problem with one of the rig's condensate pumps.
And condensate injection pumps tripped more than any of the equipment. No panic. We knew we needed to get it back on because it was going to start affecting production.
That evening, Pump A is offline for maintenance, leaving just Pump B working. The same pump that's now been shut down by the alarm's trip system.
The condensate pumps were an integral part of the production facility. You couldn't have them both offline for any great length of time without shutting down everything.
To avoid a full shutdown, the decision is made to halt maintenance on Pump A and bring it back online. But what nobody knows is that Pump A has a fatal flaw. During maintenance, its safety valve has been removed, meaning that there is nothing to stop thousands of cubic feet of gas escaping into the atmosphere. The faulty pump is switched back on. Then at 9:55 p.m., disaster. A spark suddenly ignites the escaping gas, and an explosion rips through the rig. Confronted by 700-degree flames, most of the 226-strong crew are now either dead or severely injured.
the nearest analogy is the cross between Titanic and Towering Inferno. All hell was breaking loose on that. It was just a scene for hell. It's the only way you could describe it. A scene of absolute carnage and hell. Flames, explosions, debris. Things were escalating so fast at that point that it was almost impossible to take things in.
By 10 to midnight, less than 2 hours after the initial blast, the Piper Alpha is on the verge of collapse. Finally, the rig's legs start to give way, and the Piper Alpha starts to slide into the sea.
The air module was, and the rest of the platform just started drifting apart. The 3/4 of the platform just very slowly fell into the North Sea. That's my worst memory that I know for people still on it. It would have gone to the bottom of the sea.
A total of 167 men lost their lives that night. Just 61 survived.
This was a defining moment in oil and gas industry. This particular incident has changed the face of oil and gas industry. Piper Alpha, and all different kinds of regulations have come worldwide to manage things safely. Okay. Now I'll just quickly go through these things. When you talk about this incident and hazard in this, during our operation stage, we do a thorough incident and hazard reporting and investigation. This is the statistics, okay? It is a triangle which you might find everywhere. There could be around 600 incidents with no visible injury, which can lead to 30 property damage accidents, which can lead to minor injuries 10, and it can lead to 1 serious or disabling injuries. So to eliminate these top events, we have to attack the bottom events. If we can take care and plug the holes by observing the incidents or safety observations at the bottom of the triangle, then we can prevent these top events. And that is the philosophy being adopted everywhere by all oil and gas companies in the world. We do a thorough safety observations in our work. In day to day, everybody contributes in observing the safety, whether we are doing correctly or not. All the observations are recorded and actions taken in the way. If we find somebody is doing something wrong, we don't penalize, we coach them. We coach them so that they can correct themselves. Okay. And of course, if they do the same mistake willingly, there is a consequence management. But the very first line of defense is coaching people, coaching people, so that we go towards the safer environment. And that is done through this incident safety observation things. This is a kind of safety observation checklist, safety observation form. I will not go into detail. It is the actions taken, what are the observations and what are the actions taken and all this kind of things. We do some sort of this campaigning. Maybe some months we do a safe lifting campaigning. Lifting is one of the areas where a lot of accidents happen, like crane lifting and all. People come in the way and all. There's a moving load. So we do some sort of campaigning in between to coach people, to put in people's minds what are the lifting safeties they have to take care and all. So in each month we take a particular side of the safety requirements and then coach people and do some sort of competitions and all. This is all during the operations. This is the way we try to lift our safety standards. There are many lessons learned in the industry. I talked about one in about the Piper Alpha. Okay, due to paucity of time, I will not go for the other things, but we learn from safeties. These are all available in the open in the internet. You can go through that. There are mistakes done. There are permit to works not followed properly, or this whatever actions are to be taken before taking up any maintenance work was not done, which has led to many different kinds of accidents and loss of life. There are plenty of examples available in internet, which you can also go through. This is a famous one. This is Bombay High North, which caught fire, and due to a accident which was due to mistakes in operations, there a vessel collided with the riser, and it caught fire, and it led to some 12 or 13 people dead, and luckily many more escaped. More than 250 people escaped, and the platform was lost, and it was rebuilt after quite a few years down the line. This is a recent accident which happened this year only in Bombay High. Bombay High, a storm, a barge was caught in a storm. It collided with the platform, and the barge ultimately went down into water. And people who are in the water, they were recovered by Navy boats, but finally some 66 people are missing, and they were dead. So this was one of the worst accidents happened there. Why? Because in spite of storm, okay, now inquiry is there happening, but the exact reason is not known. But barge was there in a field through which storm warning was there, and as per the laid down procedures, barge should have not been there. It should have come back to Bombay in a safe location and all. So this didn't happen, and ultimately we lost 62 people, which is a very big incident when you talk about this oil and gas field. So this kind of things happening. So we have to prevent this kind of accidents and incidents. We have to keep our safety at the top of our mind. Okay, thank you very much.
Thank you, Pradeep. Thank you. Actually, after seeing the videos, it's not I don't have the mood to talk because it's such a dreadful things. And actually, those are the specialists, those are the working professionals. So they should have that adequate knowledge. That is a great thing they are having. That's why my humble salute to you. I request the participants, if there is any question, you can put forward the question.
Excuse me, sir.
Yes.
Sir, can we get some weekly assignments?
That is not to the speaker. That is to my isn't it?
Okay, sir.
Hello. I told you to form the groups just after the program. I was thinking that I will inquire. Have you formed the group?
Sir,
Hello?
actually, no, sir.
Why you have not formed the group?
Sir, you have told that you will make us divided us in the group.
No,
so
I will not divide. I suggested that I can divide it, but that then your freedom will be cut. No? Because if I feel that I will, club A with B and then not with C, but with D, then you have to follow that. That's why I have given you the freedom that you form the groups.
Okay, sir.
You form the groups, you inform me. And then after forming the groups, we will distribute what you are to, I will say that what you are to do. That is mostly the assignment and the report writing and those areas. So in the next class, please, assure that you have formed the group. Okay.
Okay, sir. Thank you, sir.
Please.
Sir, how much group we have to make?
You can make 4 groups. How many participants are there? But not all are not joining. That is a problem. That is why those are not joining. I don't know how we will judge their performances. Tell your friends to join at proper time. Okay. If there are 40 participants, then there can be 4 groups. Each group comprising 10 participants. Okay.
Okay, sir.
Any other question to the learned speaker? Regarding the topic, this particular topic.
It's a difficult topic, HSE.
Sir, you have
But it
told
is
that.
only common sense.
Sir, I have a question. Sir, I have a question, sir.
Yeah.
Sir, you have told that in a three-phase separator, if there is any fire, then how could we prevent that?
See, fire in the separator means outside fire, okay?
Yes.
If there is a fire outside, what will happen? Okay, fire has happened due to some other reason. So fire will heat the separator and it will boil that liquid inside. So it will ultimately pressurize the separator. So separator pressure can increase and ultimately it can fail the separator. So that PSV, pressure safety valve, which is there, so that should take care of that pressure. When the pressure increases beyond the PSV set pressure, that will release. But before that happens, what happens is most of the cases, okay, that PSV is a regulatory requirement, API requirement that you have to provide the PSV, and PSV has to take care the load which is coming due to fire. We call it fire case load. But most of the time, what happens is that separator wall fails due to fire, due to very high temperature before reaching that PSV pressure. This is what happens. So what we do in the design is, if there is a fire, the fire detection is there outside, immediately we isolate the separators, inlet and outlet, all we isolate. So first of all, we cut off all the supplies, either from inlet or from the outlet. And then we blow down that separator. That separator has a separate valve, blow down valve, going to the flare line. We blow down that separator so that the pressure goes down. Now, separator on fire, it is getting heated, but we have blown down, so we have removed the pressure from the separator. So even if it fails, it will not fail catastrophically because pressure is taken out and most of the things have gone out. It will not burst. Okay, so that will happen. So this way we will mitigate. This is called mitigation only. Fire is there already. Okay, we cannot do anything. So how do you mitigate? The consequences is that we blow down the separator, make it zero pressure, so that even if the separator fails, it will not fail catastrophically. Second thing is that there are other firefighting systems which is put on the separator, like sprinkler. It will sprinkle cold water and all, okay, or water on the separator to keep it cool to whatever extent possible till the time we bring this fire in control. So fire, maybe for some other reason, we try to control that fire. At the same time, we try to put water on the separator, control that separator so that it doesn't fail. And third is we depressurize the separator. So all these actions are taken on detection of fire. So this is the way we try to mitigate. So this is on the right side of the bow tie, because fire is already there, top event is already there. So we are trying to put all the barriers on the right side to mitigate the consequences, that it doesn't fail catastrophically, it doesn't kill people, it doesn't create too much of problem on the asset.
Okay.
Good question. And there is a requirement, this API code about this fire case scenario, how to take care of that. Yeah.
And sir, in the pipette alpha, sir, while the safety valve is in maintenance, they why did not put any other measures?
Yeah, see, that valve, that pump was under maintenance. So permit was issued for maintenance of that pump. Once the permit is issued, and the permit was live, okay, permit was live means, as we said, that job could not be completed that day, and this is allowed. If it is not completed that day, next day again it will be started. So this permit is live. Permit is live, pump is not available. End of the story. The next shift who came in the night, they were knowing this, but probably they were not knowing that this safety valve is taken out. So there is a communication error between the two shifts, that permit was not properly handed over. Okay. And safety valve is taken out. It was not known by them. And they went and started the pump. First of all, since the permit is live, anybody, any shift who wants to go to start that pump has to do a thorough check from start to end that everything is there, because permit is live. So they have to close that permit. To close that permit, the first thing they have to do is a thorough check. We call it walkthrough. From inlet, outlet, everything. Had they done that thorough check, they would have found out that safety valve is not there. But they were in a hurry because the other pump stopped. And since the other pump stopped, it is a very high producing platform. So they were in a hurry to start this pump. That's why they didn't do that. So this was a failure of the permit system and the handover between the crew. 12-hourly crew changes between the crew. This failure of handover, and ultimately it killed more than 160 people. So this is a big failure in the permit to work and handover system.
Yes, sir. Yes, sir. Thank you, sir.
Welcome. Good
Okay.
question.
Okay, so our next speaker has already joined. So thank Mr. Pradeep Singh Sharma.
Thank you. Thank you very much.
And let us invite Mr. Mirza Altania of our Indian Oil. So, Mr. Mirza, please open your video.
Yeah. Good evening, Swamiji.
Yes. So, Mr. Mirza Altania, so he was a product of our chemical engineering department at Heritage Institute of Technology. He passed out in 2006, and he was among the first 5 in the, list of toppers in the department. So he has experience in Paharpur cooling towers for 1 year, and also he has the Reliance. He worked in a monoethylene plant. So this is his 2 years experience in petrochemical industries. And then he joined IOC. 12 years he is having experience there in petrochemical and refinery experience. Presently working as production manager in delayed coker unit, and also involved in commissioning of a monoethylene plant, Panipat refinery, and a delayed coker unit of Haldia unit. So with this, I request Mr. Mirza to have his discussion and the presentation.
Yes. Thank you, Swamiji, for such a good introduction. Actually, I'm here to just share my experience of both petrochemical as well as refinery. Should I share my screen now?
I think Mr. P.K. Sen Sharma, you have to remove the sharing so that next speaker can put in.
Am I still sharing?
Yeah. You just stop sharing it. Now it's free.
I have to press some button, I think. Okay.
Yeah.
Okay.
Okay. So,
stop sharing.
is the PPT like viewable?
Yes, sir.
Okay, fine. So I'm here to just share my experience in a delayed coker unit. I'm not here as a say a representative of a company or organization. Since I've been working in delayed coker unit for the past 4 to 5 years, I've had some experiences in this unit. Delayed coker unit, the first question is comes into our mind is why delayed? Okay, so we'll come to that just in just a few minutes. Before that, I'd like to show some picture. This is basically 4-drum coker drum, delayed coker unit. Here you can see there are 4 drums are there. Okay, generally there are one drum is in line, the other drum is in offline. Okay, so what is delayed coker cooking? Delayed cooking is basically a thermal cracking process where we heat up the vacuum residue, say from temperatures of 300 degrees to 500 degrees, where the cracking takes place. And due to that cracking, the heavy petroleum residue, it converts to liquid, gas, and our byproduct, that is the coke. Okay. Now, what happens here? Whenever we are heating up this vacuum residue, say from temperatures of 300 to 500 degrees, whenever it achieves this 440, 450 degrees Celsius temperature, it starts to crack. And the coke formation already takes place inside the heater where we are heating this vacuum residue. So our intention is to delay this coking that is taking place in the heater. Since we are getting the temperature of 500 in the heater, our pot that we maintain is 500. Our intention is to delay this coking that is starting in the heater, from heater to the coke drums. Now, as you know, our feed is basically the bottom of the barrel feed, means whatever the vacuum distillation unit bottoms comes, that is sent to DCU, delayed coker unit. And our intention is to cater to the demand of middle distillates. Middle distillates in the sense that our gas oil, light gas oil, heavy gas oil. As I've said, thermocracking is a simple and it is also a cost-effective process where not too many, it is where we don't require the catalyst, okay, to control the reaction. It's basically raising the temperature and initiating the cracking of the vacuum residue. Okay, you can go through this. I'll just, as I have already stated, there are, like in thermal cracking, what we do, there are generally two types of reactions. One is the decomposition of larger molecules to smaller molecules. And the second one is it further cracks the smaller molecules, further cracks to give us the heavier products, that is the coke. The byproduct, as I've already said, is the petroleum coke. CCR, whenever we are taking feed in DCU, we generally take a note of the CCR. CCR is basically conduction carbon residue. It gives an indication of the coke yield in the feed. Whatever feed that we are getting, how much its yield, as I can say we are getting, our unit throughput is say 200 tons per hour of vacuum residue. So our yield, if you say, it will be around about say 25 to 30% based on the CCR. Our CCR may be 21, 22, or it can go up to 30%. Okay. Our ultimate goal is to increase the distillates and minimize the coke. Okay. Now you must be surprised why I have put up this picture here. So this is basically a pleco which we keep in our aquarium. Its main purpose is to keep the aquarium clean and gobble up anything which is inside the aquarium, whatever waste is there, or which cannot be taken by the other fishes. DCU is somewhat like that. It is able to process a lot many streams. As you can see, first, our main feed that we get, that is the vacuum residue. It is coming from the vacuum distillation unit, VDU bottom. Okay. Second, we can process reduced crude oil. We can process slop. Slop is basically whatever off-spec material that we generate during startup, shutdown, or during maintenance of any unit. That slop we can process. Sludge. Sludge is generally only processed by DCU. Sludge, it is very difficult to get rid of in refineries. Sludge can be processed in DCU, and it can be it is one of the most efficient and cost-saving things that is done in DCU. Okay. Sludge processing. We are also able to take the clarified oil that comes from the FCC. Along with that, we can also process FO, fuel oil, bitumen, that can also be processed in varied proportion. Okay, the blending can be done of FO and bitumen in DCU. So these are all the variety of feeds that we can take. Catalyst unit may not be able to take these feeds simply because there may be impurities in those feeds. which the catalyst will not be able to sustain its selectivity activity. But DCU can process these. And now, what are the products? The main products from DCU are like lighter gases, the fuel gas, the LPG. We have stabilized naphtha, light coker gas oil, heavy coker gas oil, and our byproduct, that is coke. These are the main equipments. Let me just go through it. This is basically, if you see, our vacuum residue. The vacuum residue through a feed surge drum in the storage vessel, it comes to the main fractionator. This is known as the coker main fractionator. Okay. From there, from the bottom of the coker fractionator, we are there's a heater charge pump. At the bottom of the coker fractionator, we have heater charge pump, which delivers the VR to the heater, coker furnace. Here we are increasing the temperature of the feed, say from 280 to 300, from 280 to 300 degrees Celsius to 500 degrees Celsius. That is the outlet of the furnace. We generally term it as coil outlet temperature. That we maintain around about 500 degrees Celsius, and we vary it as per the coke yield and other parameters. From the coker furnace, from the outlet of the coker furnace, that the VR is sent to the coke drums. As I have said, one of the coke drums will be in operating mode or inline drum, where we will be feeding the VR continuously, and the other coke drum that will be in the cooling cycle, cooling cutting cycle. There is an entire cycle for that. I'll come to that a bit later, but just consider that one line will always be in operating mode, the other one will be in offline mode, where we will perform a set of operations, and the final step will be cutting of the coke from the drum and readying the drum for being in line in the next cycle. We term it as cycle. Cycle in the cycle, we term is a cycle because this is a batch process where one drum is in line for say 20 to 24 hours, and the other drum that will be in line, that will be offline for that same amount of time, and after 24 hours, the offline drum will again be in service. Okay. Now from this inline drum, the top of the inline drum, the vapors that are generated, that will again be sent back to the coker fractionator where distillation takes place, and from the top of the coker fractionator, we are extracting fuel gas, LPG, and we are sending it to the gascon section, that is the gas separation section. We are also getting coker naphtha, LCGO, light coker gas oil, and heavy coker gas oil. Okay. And the coke will be deposited in the coke drum. Okay. In order to, once the drum is offline, in order to get the coke out of this drum, we have a coke cutting mechanism where we use the high pressure jet that is at a pressure of around about 350 kgs, 350 to 400 kgs. We generate that pressure with the help of the jet water pump or coke cutting pump, as we call it. At that pressure, using the water jet, we are cutting this coke, and from the bottom of the drum, we are putting the coke in the coke pit. There is a pit which is dedicated for collecting this coke, and that coke pit is generally designed for say 15 days of operation. So it can contain up to 15 cycles of this drum. Now, the product quality, we can control the product quality and the yield pattern by changing these parameters. Those are temperature. By temperature, I mean the coil outlet temperature. Whatever temperature that we are maintaining in the heater outlet temperature, we can control the coke yield and the gas generation with the help of the cot. We can also control the drum pressure. If we control the drum pressure, we will also be able to control the coke yield as well as the gas makeup. Recycle ratio. Recycle ratio, our aim should be to decrease the recycle ratio. Recycle ratio is basically, it is a ratio of whatever feed that we are sending to the heater divided by our vacuum residue. That means whatever fresh feed that we are getting and whatever feed we are sending to the heater, it's a division of that. So basically whatever excess wash oil or whatever excess gas oil that we are putting in the system, that counts as the recycle. Okay. So our aim should be to decrease the recycle. Generally it is 5 to 10% recycle ratio. It comes around about 5% to 7% in practicality. As I have said, once we are increasing the coking temperature, the coke production and the liquid yield, that will decrease. Okay. Now, there is one negative point to that also. If we continuously increase the oil outlet temperature, that is the furnace outlet temperature, then we are also compromising on the heater run length. Heater run length, what do you mean by heater run length? It basically means that once we start the cooker and the heater is in operation, if we continuously, like if you do not control the cot or if we increase it very abruptly, the coils will get cooked up very quickly. Okay, so there is a optimum point at which we keep the coil outlet temperature. And again, if we increase the pressure and the recycle ratio, it also increases gas and coke makeup. As I've said, recycle ratio is defined as the composite feed to the cooker heater by primary feed to fractionator bottom. That is the recycle ratio. Okay, this is just a chemical reaction. I would go through it. Okay, it's basically the thermal conversion of organic materials to carbon, coke. And this is again the chemistry you can go through. You can have the PPT after this presentation. You can go through it. I will come to the process. Basically, as I've already explained. Okay, once again I'll go through it just for your convenience. This is the vacuum residue which is coming to the main fractionator. It goes to furnace. From furnace, it goes to the coke drum. One drum is in line. Okay, the other is offline. From this coke drum, there is once the vapors comes to the fractionator, then the fractionation takes place, and we are getting all these products: fuel gas, LPG, coke and naphtha. There is another section that is the blowdown section. Generally, what happens in the offline drum during this, as I've already said, there is a 24-hour cycle for converting that offline drum ready for cutting of coke. So there is some processes there where we do the steaming, we do the cooling. These are all the processes which takes place for making this drum ready for cutting. During that process, when you are using the steam, whatever oil or whatever VCM content is inside the coke drum, inside the coke, that is all stripped to this blowdown section. The reason for having this blowdown section is for environmental reasons, because these VCM, whatever oil and VCM is there, that we cannot simply flare, put in flare, or we cannot vent it to atmosphere. So this blowdown section is there to take care of that, so that there is no environmental atmospheric emission is there. As I've said, it's a batch come continuous process. Batch in the sense that our coke drum operation is a batch process. Continuous in the sense that our gas con section, the downstream section, that is running continuously because it is processing the lighter materials, LPG, then fuel gas. Okay, our flow through the furnace coil is continuous. This is very important. Whenever the heater is in operation, there should always be flow through the furnace coil, and that flow should be, there is a particular velocity that should be maintained inside the coils. Generally, means in any licensor specification, be it ABB Lummus or say for Foster Wheeler, in any licensor specification, there is a provision for velocity condensate injection into the coils of the furnace. Okay, inside the coils of the furnace where we are putting the VR, there we also inject velocity condensate. It is basically the purpose of putting that condensate is to maintain the residence, to increase the velocity of the fluid and decrease the residence time of VR inside the coils. We have to decrease the residence time inside the coil simply because we want to delay the cooking inside the furnace and push it towards the coke drums where it gets the residence time for coke formation. Generally, we maintain around about 1.8 to 2 meter per second. That is the standard velocity that is to be maintained. Okay. And this velocity condensate that I'm talking about, it is a very critical parameter which is monitored very critically during our day-to-day operation. At no point of time should this velocity, means the VR flow, vacuum residue flow, plus this velocity condensate flow, that should not come down. Okay. If there is a decrease in the vacuum residue flow, that is our VR flow, then we have to increase the velocity condensate to compensate the decrease in the mass velocity. Okay, so for that we have to critically monitor the velocity condensate flows. I've also said feed is switched between the 2 or more drums. Generally, we have we can have 2 drums, we can have 4 drums, 6 drums, 8 drums. Okay, but it will be in pair because one will be in line, the other will be in offline mode. So we'll have drums in pairs, 2 or more. Now, as I was saying earlier, in delayed coker unit, we go by the cycle time. This cycle time basically indicates the time during which the coke drum is in line and the other coke drum will be in offline mode, and during that time there will be certain steps which will take place to make that drum ready for cutting, and after cutting we'll prepare it for coming in line with the process. This is some write-up is there, you can go through. Okay, just as I've said, this vacuum residue is coming to the main fractionator, and from this we produce high-value products such as gasoline, diesel fuel, LPG, petroleum coke. Okay. FG and LPG are recovered, and naphtha is also fractionated here. LCGO and SCGO, these are 2 products which are generally sent, like LCGO is sent to the diesel pool, or it is sent to the hydrotreating unit for further treatment. SCGO is generally sent to FCC, or it can be sent to hydrotreating unit as per refinery configuration. Okay. This is a coker furnace. This is basically the heart of delayed coker unit. Okay, the coker operation is the most critical thing to watch out in DCU. As I've said, there's always a temperature, coil outlet temperature band is given through which we have to operate. Okay, it can be say 495 to 505 degrees Celsius, or as per the feed that we are getting as per licensor specifications. As I said earlier, this steam is injected to minimize the cracking until it is in the coke drum. Okay, that is the velocity condensate. What it does, it basically turbolizes the fluid. Okay, and it increases the mass velocity. So there is the cooking tendency inside the coils. Inside the furnace, there are coils. So the cooking tendency inside the coils of the furnace is minimized. If there is a variation in the velocity condensate, suppose it decreases for some say pump issues, or there is some issue with the instrumentation, at that time there is a provision for shutting down the unit and injecting emergency steam. There is a high pressure steam is there that we have to inject inside the coils to remove whatever coke is inside the coils. Otherwise, at that temperature, at 500 degrees Celsius, all the vacuum residue is whatever is there inside the coils, it will cook up and it will be a big trouble for the unit. Okay. So at any moment of time, there should always be a certain velocity of the fluids inside the heater coils. If the velocity cannot be maintained, then we have to shut down the unit and we have to flush out those coils, flush out the coil with the help of the emergency steam, that is high pressure steam, and we have to remove whatever residue is inside the coils to prevent cooking. As I was saying, these are the heater coils, okay, and these are the burners. Using fuel gas, we light up the burners and we control the coil outlet temperature. There are in the heater monitoring parameters. One of the parameter is this flame. There should not be any impingement of these flames on the tubes. If there is impingement of the flames in the tubes, there may be localized coking inside the coils, which may lead to blockages in the pipe, and we may have a condition where the entire flow is getting disturbed, or it may get totally choked off. So that is one of the regular field rounds checking that we do. So this is again what I have right up there, what I said earlier. In the offline drum, what we do, we basically do the steaming. After it is taken out of line, first we do the steaming. Then after that, there is cooling is done. And after cooling, once the water means the drum is cooled, then we open the unheating devices. By unheating devices, we mean at the top and the bottom of the coke drum, we have got two automated unheating devices. The picture I'll show later. So what happens for cutting, we need to open those unheating devices that are at the top and bottom. In say 15 years ago or 20 years ago, we did not have the provision of automated unheating devices. But nowadays we have these automated unheating devices where there is very little manual operation. From a safe height, a safe location, we can open these unheating devices through PLC driven logics to safeguard any untoward reaction. What wrong can happen while opening this unheating devices, I'll show a bit later. Okay, it was a big safety hazard, and in fact there were some accidents also which took place due to wrong opening of the unheating devices. I'll tell you a bit later. Let us go to the next slide. Okay, so these are the coke drums. Like I said, coke drums can be in pairs. They will be in pairs, either 2 drums or 4 drums. This portion, this is the Kelly portion. Now, what do you mean by Kelly? Kelly is basically, it comprises of a long stem with a cutting tool. The water jet that we are using to cut the coke inside the drums, okay, this entire section, this comprises that cutting tool. Okay, there is a long pipe, and at the end of the long pipe we have got a cutting tool which controls the pressure, that is around about 350 kgs, and that helps us in cutting the coke inside the coke drum. this deheading that I said, nowadays it is automated, totally automated. It has like it has brought in a new level of safety in poker units. We had seen incidents of fire, explosion at the top of the coke drums earlier due to wrong operation. But now this is a hazard point. Basically, as time went, refineries understood the importance of this automated heading devices, and in old refineries also, they are planning to change their system from manual unheading devices to automated heading devices. This is the unheading device. Basically, what happens here? This is the bottom of the coke drum. Here, this is the BOD. We call it BOD, bottom unheading device. There is a long plate which covers the bottom of the drum. When we need to operate the unheading device, that is when we need to open the unheading device, either the unheading device is moved by electrical force, by motor driven operation, or it can be done by hydraulic pressure. Okay, and this is totally automated system. So there is no there is very little chance of this unsafe act by any person. Coke drum cutting and handling. I've said that they're using this high pressure cutting water. We are cutting the coke, and all the coke it goes into the coke pit at the bottom of the coke drum. So just to recapitulate, in the hydrocarbon side, the flow that we have initial feed. It goes to the heat exchangers for this preheat. It goes to fractionator column, main fractionator column. Then it goes to the heater. From heater outlet, it goes to the coke drum. And again, the vapors from the coke drum, it comes back to the fractionator where the distillation takes place, and this the products that we get that are sent to the gas con section. From the water side, that is the coke cutting system, we have the coke cutting tank where we store the water, cutting water, and from there using the cutting water pump, we do the cutting operation in coke drum, and whatever water that goes into the coke drum, from the bottom of the coke drum, it goes to the coke pit, and again it is recycled back to the coke cutting tank using a maze where we have a pump which pumps the water back to the coke cutting tank. These are the main three sections: fractionator section, coke drum section, and gas con section. Okay, fractionator section contains the main fractionator. Coke drum section contains the heater, coke drum, blowdown section. Gas con contains our compressor, stripper, absorber, sponge absorber, amine scrubber, debutanizer from where we get the LPG, our naphtha splitter. Naphtha splitter basically we are getting the light naphtha and heavy naphtha from this column, and LPG amine contactor. Here we are getting the LPG. We are like sweet LPG. We have the amine circulation going on in the column, and from there we are removing the S2S, and we are getting the sweet LPG from this column. So this gas con section, this is always, it is always in operation. Okay, the coke drum section, it is in batch process, and fractionator section is also in continuous operation. From the fractionator section, we are getting SCGO, LCGO, naphtha, LPG. Like I said, heater section, it is providing the heat to feed the VR, vacuum residue, for thermal cracking. Coke drum, the entire reaction takes place in the coke drum where the polymerization takes place and coke is formed. In the blowdown section, as I have said, it is basically an environmental norm requirement where we have controlled the emission and recover the hydrocarbon vapor from cooling and heating cycle of the offline drum. In the gas con section, we are from the lighter feeds that are coming from the main fractionator, we are stripping off this lighters from the heavy cut, C3, C4, C5 cut. We are getting the lighters FG. In the absorber, we are basically it acts as a trap to get the LPG, and naphtha is used as a lean oil. It is used as an absorbent in this column. We have the sponge absorber. Sponge absorber is basically to recover the carry away C3, C4. And we have the FG amine scrubber, where again the fuel gas that is coming in contact with lean amine, and the H2S is removed, and the fuel gas devoid of H2S is sent to the fuel gas header. Debutanizer, basically debutanizer, here we are stripping out the LPG. Okay, we are getting the LPG from the heavy part, and this LPG is sent to the Minox unit for further treatment. Light and heavy naphtha separated in the naphtha splitter section. Okay, so this is the last column. This is the last section in our DCU, the naphtha splitter section, where by steam stripping we are getting the light and heavy naphtha. LPG amine contactor, as I have said, it is the sweetening of the LPG in amine contactor. Amine is used as an absorbent, and it removes the H2S from the LPG. Further H2S removal is done when this LPG that is coming out of the amine contactor is sent to the Minox unit, where further H2S is removed and mercaptans are also removed from that section. Okay. Now, this is the coke drum. This is the inline drum, and this is the offline drum. Let us consider that. These are all the automated valves. Actually, entire operation of this coke drum is based on the PLC, and all the interlocks are there. As Mr. Pradeep Sen Sharma ji has earlier said regarding this HAZOP and SEAL study, with HAZOP study and everything, this area, now this is totally driven by interlocks, PLC driven interlocks, which are quite safe, which does not allow any misoperation. Okay, the system is configured in such a way that the interlock will prevent any unsafe condition. Say, let's take an example. This is the inline drum, and this is the offline drum. Say V02 is the offline drum. Somebody comes and say tries to operate this vent valve. This is the vent to safe location. There is a vent valve is there. Someone tries to operate the vent valve of the offline drum. He will be able to do so. Okay, the interlock will allow him to do so. But in case of this inline drum, this V01, the drum which is in inline, that drum, he will not be able to open this vent valve. There are safety interlocks. For example, to open this vent valve, the temperature of the drum must be below, say, a certain temperature. The pressure in the drum should be below a certain like specified pressure. Okay, it should be below the normal operating pressure, much below that. So there are a lot of interlocks are there which prevents the unsafe operation, manual like errors, to prevent the manual errors, and it it does not allow any catastrophe happen. Okay, so all these valves, we call these as vapor valves. Why do we call it vapor valves? Because the vapors from the drum that goes through this SP1A. Why we call it SP? Because all these valves have got steam purging inside it. In the cavity of these valves, there are steam linings are given, steam purging is given, because with time, these lines are also prone to coking. Okay, these lines are subjected to temperatures of around about 430 degrees, 440 degrees, and coking may also take place here. So in the cavity of these valves, there may be coke deposition. So in order to disperse those coke and to prevent the coke deposition inside the valves. Okay, so steam purging are given, which removes the coke and keep these valves healthy. So that's why it is known as SP valves, steam purge valves. Okay. So from these drums, the inline drum, the vapors goes through SP1A, SP2A, and then is go and again goes back to this is actually this is wrong. This should be main fractionator. It goes to main fraction. Okay. Now let us go to the next slide. Okay, now this is interesting. This is the drum cycle time. As I said, the drum cycle time can range from like 16 to 24 hours. One drum can be in line for say 16, minimum 16 hours to 24 hours. During that time, we have to perform these set of operations in the offline drum to make it ready for switching from the offline to inline. What are the first activities? Whenever a drum has gone offline, first of all, we put the steam in the coke drum, and that steam along with the oil, whatever oil that we can recover, it goes back to the main fractionator. Okay, this happens for half an hour. Okay, just take in consideration that this is for 18-hour cycle. If we consider 24-hour cycle, then this cooling period, that is low range cooling and water quench, this cycle time will increase. Okay, this will increase to say 6 to 7 hours, maybe 7.5 hours. Okay. So the first step is steam to fractionator. Whatever steam that we are putting, that will go to the coke drums to recover the oil inside the drums. The next step is steam to blow down section. What is the requirement of the blow down section? Because we need to strip out all the VCM material inside the coke drum to this blow down section. Okay, that takes place for 1.5 hours. After these steps, we come to the cooling of the drum. Since the drum is operating at say more than 400 degrees Celsius, okay, so we need to cool that to below say 150 or 130 degrees Celsius, okay, for the cutting operation to take place. So this we are using the water to cool down this drum, and that cooling operation will take place for say 5 hours. After the cooling operation, then we depressurize the drum and drain the water. Okay, we drain the water, and that water again goes back to the cook cutting tank. After that, we unhead the top and bottom cover of the drum. Okay, now the drum is ready for the coke cutting operation. The top and bottom covers are open, and the drum is now cooled down. Now we'll use the coke cutting pump. We'll start the pump. Our Kelly system will be in operation, and using 350 kgs pressure water jet, we'll start cutting the coke inside the coke drum. Okay. After this, once the cutting operation is over and the coke is removed from the coke drum and the drum is washed with water, then we go for again reheating. Means we have to close the top and bottom unheading device, and we will pressure test. Means we'll pressurize the drum to the normal operating pressure, that is around about 1.5 to 2 kg, a bit more than that, 2 kg, and we'll check for any leaks. Because we have opened the unheading device, there may be some the unheading device may have some leaks, or the flanges may have some leaks. Okay, so we will check the entire system with this steam. We'll pressurize up to 2 kg, 2 or 3 kgs, and we'll check the entire coke drum for any visible leaks. After that, we will put the drum in warm up. Warm up means both the drums, drum 1 and drum 2, both will be in heating operation. Both will be in line for 4 hours, during which the offline drum that will be heated to a certain temperature. This is done because we are operating the drum at a say temperature of 400 degrees. Once we have cooled it down to 130, we cannot inject the VR directly into the cool down drum. That will lead to some foaming, or it may lead to some absurd condition inside the drums. So we have to first heat up the coke drum. So that is why we are doing this warm up or vapor heating. Once the drum temperature reaches a certain 200 or 250 degrees Celsius, then we go for the switchover. What do you mean by switchover, changeover? It means that we are switching from the online drum, say V01, we are switching from V01 to V02, where the vacuum residue is switched from one drum to the another. Okay, so once the offline drums comes in line, then this same cycle, this same procedure will take place for the V01 offline drum. Okay, so this is basically batch process. One will be in line, the other will be offline, and this activity will take place every day in every cycle. Okay, now our byproduct is coke. What type of coke do we produce? Generally, there are three types of coke that DCU produces. One is sponge coke, other is short coke, and the third one is needle coke. Needle coke is the premium coke. It is one of the best quality cokes. But to produce needle coke, we have to have certain parameters, like we have to go for higher drum pressure, low sulfur. Okay, so these conditions we have to meet. Generally, in refineries, it is tough to make this needle coke simply because the initial designing of the delayed coker is based on sponge or short coke. Generally, we produce short coke or sponge coke. Okay. For needle coke, we need some specialized, we need a drum capable of handling higher pressures. We need very stringent feed parameters. Okay, so this is basically sponge coke that we have. Looks more like sponge, so that's where the name comes, sponge coke. This is short coke. Short means these are like short pellets. Okay, so the name comes from there, short coke. And these are the needle coke. Okay, now hazards. We have gone through all the important parameters, how to keep the unit safe. Okay, but these are the hazards which takes place in the unit. We are dealing with auto ignition temperature fluids. The temperature that we are operating, say above 300, 350 degrees Celsius, those are all auto ignition temperature for those fluids. Any leaks in the line, or say from any flange or any pump seal leak, okay, that will lead to fire in the unit. So we have to be extra cautious, and our monitoring should be very stringent to identify first any leaks and to take immediate remedial measures. There are high prone zones, high fire prone zones in the unit. The coke drum top, as I have earlier said, this is a very high fire prone zone simply because any incorrect operation or any leakages may lead to a huge fire. This incident, this happened in one of the, I think it happened in America. What happened was the operator went and he manually opened the top unending device of the inline drum. Okay. And at that time, the interlock that was given there, means that were present in the unit, did not fully cater to the condition where an operator can mistakenly open the top unending device. There was some parameters like interlock action was there, but it was not foolproof. So by mistake, he opened the TOD of the inline drum, and all the vapors, hydrocarbon vapors, everything came out, and there was a big fire. Okay. After this incident, there was a committee was there which went through this incident, and they suggested addition of means a number of additional interlocks to be provided in the system, in the top monitoring device to prevent such incidents. So this is one of the hazards in the unit. This is rather I would not say it's a fire hazard, but this is one of the very tough situation that a production guy has to face in this unit. It may happen. This is basically a tarry fluid from the drum. If there is power failure in the unit and the coke drum, inline coke drum has been in operation for say few hours, say 2 to 4 hours, there is a possibility that inside the coke drum, instead of coke, we'll have this tarry type material. And to get rid of this tarry type material, it is very tough, and it will take say weeks to get rid of this tarry material from the drum. This is one of the worst case scenarios that can take place inside a coker unit. So we have to be very careful, and in emergency situations, we have to follow certain protocols to avoid this type of situation. You can see this thing inside the drum. It will be very difficult to remove all this tarry material from the drum, even with say continuous steaming or say cooling or say with the coke cutting pump and Kelly operation. It will take weeks. Sometimes it takes weeks, even months. So this is another hazard. This is the immature coke drum, where the VR that is going, that has not matured enough to produce coke. So this was basically a brief overview of DCU. Okay, there are a lot many things to say, but I guess I've been able to give a brief description of the unit and the important equipments. So if you have any questions or queries. Shamiji, have they been to any?
Yeah. Can I ask one thing, Mr. Mirza Alpunia, that when delayed coker unit was not there at Haldia till 99, you said, till 2019, you said. 2018. So how that part was addressed? I mean, what was the loss, both technically as well as financially?
Actually, we were losing out on the metal distillates. Basically, the purpose of DCU, anyway, one of the purpose of having DCU here is that we needed to improve our distillate yield in the refinery. And once DCU came, our distillate yield improved because we were able to process all the heavy materials and we were able to extract the lighter components from those heavy materials, which were earlier going into bitumen, making of bitumen. Before this, we were having the whatever VR that we are having, that was going into the making of bitumen, and that bitumen was being sold at a lower price. Now we are able to extract the lighter components from these VR, vacuum residue, and we are getting LPG, we are getting this diesel. So these are all profitable the components.
So you mean technology was there, only the delay of delayed coker unit practically had given you more benefit after installation. That
yeah, so there was a delay in delayed coker unit.
Yeah.
Okay. Is it today is the Indian Oil Foundation Day or anything like that, Mr.?
Yeah, today is the Indian Oil Foundation.
That's a great thing that we have got in.
Yeah, 62 years. Yes. 62 years celebration, sir.
Very good. So we enjoyed the presentation very much, and this is a very advanced, endeavor of our Indian Oil. So thanks to you, we learned a lot. I think the students are not having any question. Pradeep, do you wish to ask anything? Pradeep? No.
Yeah, you asking me?
Yes. I mean, do you, any queries or anything, or you can just switch on your video?
No, it's yeah. No,
Oh, I see.
it's a very nice presentation, in fact,
Yes,
because
yes. You should cheer up the youngsters because you see,
it's very nice
ultimately
presentation,
they will
Mr.
become
Mirza.
like you.
Yeah.
And I am so happy that our alumnus, Mirza is our alumnus. There are many other students also in Indian Oil and ONGC and Reliance. So many. So thanks to all of them.
Yeah. It's very well presented. In fact, I wanted to visit one of the refineries because I don't have any refinery experience. I'm on the upstream guy only. Well,
I am fortunate that I have had experience. Means I have had the opportunity of working in both petrochemicals as well as refineries. So I consider myself very.
He was there in Reliance also.
Oh, very good, very good. Then. So you have all downstream, the whole downstream gamma teams you have seen.
Okay.
Good.
Okay then, Mr. Thank you very much. Let us close this session today.
Okay.
Isn't it?
Thank you very much.
Thank you. Big hand to Mirza.